All right, cool. So today we're going to talk about data availability sampling. I can never say that word, so bear with me. Also called DAS, maybe that's easier to say. I started getting into this pretty recently, and it's kind of confusing. There's a lot of different protocols that talk about DAS or DA in like different ways, and they use it in different ways, and they're trying to solve different problems. So I think I'm going to spend most of these trying to talk about use cases and trying to build like some sort of mental model of basically like what is it, like who uses it, how do they use it, like who is storing, like you can already guess that it's about data being available, right? So for data to be available, it has to be stored. So it's like who is storing it, how are they storing it, what, and like how do you even define availability? And like defining that word is also going to be a kind of difficult, but we'll get there. Maybe before I start, do you guys know any DAS protocol? Like, do you want to throw some names out there? EigenDA, okay. Up. Let's write it down. Anything else? Blobs, okay. So we're going to call that Ethereum blobs, unless there's a different notion of blobs. So there's also blobs, right? Anything else? Which one? Wait, say that again? Avail? Yeah. Avail, right? Like the Polygon stuff, yeah. So Avail is one of them.
What's the name of Nick White's project?
Celestia is one of them. Actually, these three I think we can sort of, so I don't know how all the DA stuff work. I think these three we can put them in the same category, and I'll sort of explain that after. Hey, Kobe. So we're trying to list all the DA stuff. Anything else? Walrus, okay, very good one. All right, so I think we have a DA expert in the room because nobody knows that one. So you can help me. Which one? Shelby. Okay, I guess I don't know that one.
Is it the Aptos one?
Oh, so okay. So Walrus is Sway, Shelby is Aptos. All right, let's put them in the same category, I guess. Maybe they are, maybe they aren't. I don't know.
Iris? Is Iris doing it?
How do you spell that?
IRYS.
Oh, I'm getting a no here, so we're not gonna put that one. And okay, I'm gonna mention some other ones, but we're gonna stop here. That's already a bunch of them. So you can see that different people are trying to solve DA, and you're gonna see that we're already getting different definition of DA, and that's why I added some circles. And I'm gonna add another one here, but I'm not gonna put anything yet. So again, I haven't really defined what DA is, but you can think of it as like we have some data and we want to make it available to other people. So let's see what kind of data do we have. So if we start with blockchain, the simplest blockchain like Bitcoin or something like that, the data we have is the state of the blockchain, all the account balances, and maybe also the history of the blockchain, all the blocks, all the transactions, that if you want to sync to the network, you can get that data and as a full node, you can sync to the network. And for that kind of data, I think the solution, as far as I understand, has been sort of solved in a very simple way. Everybody replicates everything, so this is full replication. Oops. Full replication. And as long as one guy is honest and has the data, then you can always ask them and they'll give the data to you. So it's kind of we're sort of saying, okay, this is an easy problem. Everybody replicates everything. We're all good. The data is always available because of course there's going to be one honest guy. And then we started being like, okay, we're creating these chains that have more and more data. We're going faster. We're processing more transactions per second. And we're also wondering what else can we store? We have smart contracts data, that takes space. And we're also starting to be like, what if we can store any kind of data? And so that's where a number of, I don't know how to call them, like data chains or stuff like that, started. And there was the first one I learned about was Arweave. There was a Filecoin. Maybe you guys can help me if I miss one. There's SIA storage. Is there another one? I don't know.
Iris now, I guess.
So IRIS.
YS.
Okay. IRYS. Is there another one that people can think of? Yeah. All right. Anyway, so basically these guys were like, okay, we want to do more than just the data of the blockchain. We want to do like arbitrary data. I'm actually not too sure how all of these kind of guys work. I think Falcon works on top of IPFS, which is another well-known protocol. The one I looked at back in the days was Arweave. This one is pretty simple to explain, so I can give you the intuition of that one. Yeah, I use the same. Arweave basically is a proof of work, at least it used to be, and everybody's fully replicating all the data, so people can submit like, I don't know, websites and like different types of data. And to make sure that the data is available, there's this idea of continuously challenging the protocol, the network, where as in the proof of work hash, you're going to include a random offset of some random historical data. And so if you are a miner in that chain and you want to get a reward, then you have to store all the data, or at least enough of it, so that you can create that proof of work hash in time and get the reward. And so you can think of that. I'm not sure exactly, from a rigorous perspective, like what are the proof of security there. But it's a very, I think it's heuristic based, and it's a very simple model. Like, let's challenge the protocol. Let's make sure that everybody has the data. If people are not storing that data and data disappear at some point, then the protocol will come to a halt. Like, the network will stop. I think there's a timeout, but it's still pretty bad. Like, does that make sense? That explanation? Like,
Against
yeah.
what source does the chain protocol verify that you don't have the required data to participate in the
So they don't check that you don't have the data. They just check that you can present the data in your hash. I don't remember how the scheme works exactly. I think it's like a Merkle tree kind of thing where the scheme is basically you need to store the data, and it's not enough to store hashes of the data. So they use these kind of like random offsets, but they end up proving that this is the actual data that's committed. There's a hash that's committing to the data, of course, and they managed to prove that. They managed to force you to hold the data and not hashes, if that makes sense. But yeah, I don't want to talk too much about that because it's not. I haven't looked at that in like 6 years, and it's not the subject. But this is kind of we can think of that as sort of long-term, full replication DA in a sense, and the only security comes from challenging the network as part of the protocol. Interestingly, I don't know. Should I use some colors? All right. Arweave is this thing. It's like this long-term stuff. I think basically these other guys are similar in a way. I'm not sure. Don't quote me on that. Although this is recorded, but and also Walrus uses a different model, very different model, but they also do long-term storage. And I guess Shelby might do the same. But these are connected just because they do long-term storage of data. Okay, should I mention anything else there? I guess Walrus is also more interesting, I think, to me, because they have this BFT protocol, and if you have enough honest participants, they have like more of a game theory approach to it. And they also do sharded, which I'm gonna, here it is. They also shard the data. So here we have full replication. In the context of Walrus, they actually shard the data, meaning some people only store some of the data. And so it's lighter for nodes. They had some numbers, like they're storing like terabytes of data right now. And they can do that because the network, like a node in the network or validator, only stores some of the data. And they do like some clever stuff, and I'm gonna be talking about that later, which is like they encode the data in clever ways, and they do more like what we think of data availability sampling, which I still haven't introduced, so bear with me. And I'm not really gonna talk about Walrus anyway, because I don't want to talk about it today. There's a lot of things to talk about, but just so you know, it's here, it exists. That's what they do. All right, cool. I've talked about these things. Let's introduce the idea of rollups. So this is where it's getting interesting. I think DA wasn't really a rigorous thing before we started talking about rollups. There is, to my knowledge, two kinds of rollups. Optimistic rollups and zk rollups. If you don't know what rollups are, basically you can think of, at least in the context of Ethereum, the chain is slow, they cannot process as many transactions as they want to. So they're like, okay, we're gonna ask other people to process transactions in something that's faster. We've had the concept of like sidechains, which were more like other blockchains that were connecting to your blockchain. These are not sidechains. They basically don't have consensus. They just have one guy, like a centralized sequencer. Sometimes it's decentralized, but that's not interesting here. They just have one guy that orders all of the transactions and says, this is what's going to happen. We don't need to come to consensus on the next blocks or whatever. We don't need to do proof of work or a BFT or whatever. I'm going to decide what comes into the protocol. But then it's only when I settle, when I post that in a smart contract on Ethereum. So in this system, we have an L1, for example, Ethereum, and you have a smart contract here. It's only when I post the state transition. So we have a state 1, we go to state 2. And you can imagine that there's a state 1 in the smart contract. It's only when I post it to the layer 1, to the settlement layer, that these things get finalized. So no need for consensus, because we get a checkpoint of where the state is in this smart contract. So a good way to see the smart contract, by the way, is as a like client for that chain, but it's kind of like the like client. It's like the source of truth as to what the network looks like, what this chain looks like. It's not really a chain, it's a rollup, but anyway. Of course, you want to know what is inside that state transition. Actually, it's not of course, it might not be obvious. You can just submit the state transition and just be like, trust me. But we usually don't want to trust people. So we have these two. Well, actually, does this thing make sense? Maybe for people that didn't know about rollups, like this kind of abstraction of what a rollup is in the context of in this explanation, this smart contract is just giving you the new state, and you just have to trust it. It's not very secure, but presumably you have an admin key that allows you to advance the state. Yeah, does that make sense? Yeah. So, of course, we don't want to trust that state transition, we're in this decentralized context, so we don't want to trust someone. So we have two approaches. Optimistic is someone's going to post the state transition, and then there's a challenge period where people can actually verify that offline by themselves, so we can audit the protocol. And then if we realize that this state transition was incorrect, we can show that it was incorrect by executing part of the state transition on chain to show that it was an incorrect state transition. So in the optimistic case, we have users, and they can submit a fraud, what we call a fraud proof, which is, nope, that state transition is wrong. I don't believe what you're saying. And then something happens, they get slashed, the thing stops, whatever. zk is faster. There's no challenge period. Basically, what you do is that in addition to the state transition, we're going to go back to a good state transition. In addition to a state transition, you also post a proof. And so that proof tells you like there exists a block of transaction and these transactions are valid, and if you apply them, you go from state 1 to state 2. Now we're in this, so I never understand all these different distinctions of rollups. I think this is called a validium, because what happens is that you don't actually have the states as an external observer. Maybe you would know. Is that called a validium? When you don't post the...
Just you don't have the data.
Right. So you don't post the data on chain, right? So it is called validium. I don't know if that distinction really matters. But basically, you don't have the data on chain. It's somewhere. You can request it to the rollup service if you want. But it's kind of sketchy because if in the case of optimistic, if you want to create a fraud proof, you need that data. You need to be able to re-execute that state transition, so you need the data to exist. And in the case of zk, there's another, or in both cases, I guess, if something bad happens one day, you want to be able to exit this thing, and most of the time you want to be able to exit this thing, you have to provide proof that this is what you have in the account of the Merkle tree or whatever. So you can imagine this state is a Merkle tree. So to provide this proof, you need to be able to reconstruct the latest state of the rollup. And to do that, you need to be able to have access to that state. And of course, if you don't have anything on chain, you cannot reconstruct that state. So to remediate, basically all of these rollups started doing one thing. They started posting data inside here, the blocks or the transactions or whatever is your abstraction. So now every time you had a transaction that would advance the state of that rollup, you would include maybe a proof in the case of zk rollups, but also you would include the blocks and the transactions and everything, so that in the case of optimistic, you can create a fraud proof, you can detect if something weird is going on, or in the case of zk, you can reconstruct the states if you need to exit the protocol. Remember, these are centralized protocols, so we don't trust that they're going to be live. They're going to run forever. Does that make sense? Any questions so far?
So if DA is needed to store blocks for optimistic rollups, because you need to be able to challenge whatever the rollup state transition provided by the fraud proof, what's the need for DA in zk case?
The need for, so I didn't really call that DA, but sure we can, so let's call that DA, right? The data is available, we need it to be available, and it's available because we have to post it on chain when we post these state transitions. In both zk and optimistic, if something bad happens, like the admin of the smart contract, for example, stop posting new data, or in the case of optimistic, they fucked up, maybe you want to stop the protocol. Like you want to say, okay, let's do a mass exit. We're stopping the protocol, this thing is dead, but we still need to allow users to withdraw the funds from the L2. To withdraw your fund, you're going to have to submit a proof that you own, 50 Starknet or whatever. There's a bunch of rollups. And so to do that, usually you need to be able to reconstruct the state, that Merkle tree. And to be able to reconstruct the state, you need to look at the historical data. So here, you can look at the historical data of Ethereum. You can just look at Ethereum. And you'll see these blocks being posted in all these transactions historically, and you can reconstruct that state by just running all the state transition yourself. Does that answer your question?
Yeah. So basically you're saying you need the data to be able to draw from whether it's optimistic or
not. Yeah. If bad things happen, usually bad things don't happen. Although for optimistic protocol, you need auditors, right? You need people that audit the system, so they need to have access to the data. But in zk rollups, most likely you're never gonna use that. You're never gonna access that data, because hopefully bad things are never gonna happen. So this is really a last resort kind of thing, which is also important because when we're looking at Walrus or Arweave and these kind of things, we're not talking about last resorts. We're talking about people are actually gonna try to retrieve that data, so we need schemes that allow the data to be retrieved efficiently. But in these cases, especially for zk rollups, you don't care if it takes time to retrieve the data because most likely you're never gonna make use of that feature. Okay, so what's interesting is that I think the first time DA was kind of written in a paper and explained and everything was in the first optimistic paper. Fraud proof, and I can't remember the name. And so they were okay, they stated that problem, and I'll say that. And then people observed that in practice when they started deploying these rollups, posting that data on chain was very expensive. People compressed that data and they serialized it in a way that was cheaper to post it on chain, but it was still pretty expensive. Most of the costs of these rollups apparently came from posting that data. So, of course, you had Validiums that didn't post the data, but it wasn't clear if people wanted to trust that model or not. And so people started thinking about, okay, how can we make the data available without incurring this cost. Okay, so this is sort of, today when you think of data availability, a lot of it is trying to solve that problem. Maybe half of it is trying to do long-term storage and whatever, but a lot of it is also trying to figure out short-term storage of that data. Short-term because we only need to make sure that the data is available for people to have time to create fraud proofs or for people to have time to recreate the states. But we don't need to, it's okay if it's not available after some time. So the sort of solution to that was to look at these datachains, which are like basically other L1s, they're blockchains, and they will, and I'm mostly talking about Celestia because I haven't looked too much into how the other one works, although I think Avel also work pretty much in this way. You have consensus, they have their own network, and you're just posting your data there. They don't know what that data is, right? Usually it's roll-up data. And they will basically make sure that the data is available for you. And the proof that the data is available is basically like a BFT proof, so it's a bunch of signatures. And so here, what you would put inside of that is like a DA certificate, let's call it like this. So in this case, it's a bunch of signatures from the network that tells you it's a BFT consensus, so there's a game theory thing. They have full replication anyway, so as long as one honest node is here to give you the data, it's fine. And they store the data for, I believe, like 30 days.
Celestia still does full replication?
Yeah. So they're moving to a different system from what I've heard, and I'll briefly mention that, but that's a good point. These chains also do something interesting, and so that's where the sampling comes here. And it is very similar to what I was explaining with Arweave. Actually, Walrus also has that. So it's a concept that you can think of as a, where can I write that? You can think of this concept as like, and they also call it challenges. But it's sort of sampling, and you'll see what sampling is we'll define it a bit differently after. But remember in Arweave, the protocol challenges the fact that people are fully replicating the data. In Walrus, there's some sort of challenge, like it's sharded, but the protocol will make sure that you're actually storing what you're supposed to store, your shard. And there's a challenge, they'll challenge you during there's challenge periods. So there's something similar. In Celestia or these datachains, it's a bit different. They allow people to challenge the network. And so as a node, you can come and you can ask different people in the different nodes in the network, usually only for data that's in the last 30 days. You can ask different nodes, hey, do you have like some of that data here or some of that data here? And you can get some guarantee that the data is stored in the network basically based on people trying to challenge by themselves the network. I think that's all I'm gonna say about that. I think it's interesting. It's an interesting model. But yeah, this is how datachains work. Ethereum looked at that and was like, okay, I think we can do something where we have that, like you don't need, everybody is gonna move to these datachains, or I don't know what they were thinking, right? But I imagine the boss of Ethereum, I don't know, Vitalik was like, oh my God, everybody's gonna use these datachains, we're adding another trust assumptions. Maybe we can do something where we add DA on Ethereum. And we do this other protocol that's basically cheaper, and we will store what they call blobs. And I guess different people started calling these blobs as well. But you can think of blobs as like opaque data that we're going to store for you. And in the case of Ethereum, they store it for around 18 days. And so instead of a DA certificate here, they added some instructions in Ethereum. And basically, if you submit, this is a transaction, right? is your little transaction. If you submit a transaction to the network and you submit a blob, the execution of the smart contract is going to execute your transaction, right? And they're not going to see that blob, but you're going to be able to refer to the blob with an instruction as by its hash or something like that, only if it was included in that transaction. And then part of the network is going to make sure that this blob is stored for 18 days. And I'm going to explain how that works. Yeah, so what's interesting also, I can mention that, but I believe there's like, every block in Ethereum is like limited to 9 blobs, I think, today. And so, if you have like 9 rollups that are trying to submit blobs as part of these transitions, then they will like maximize the capacity of a transaction. I think some people have looked at that and it's pretty underutilized. So it's pretty cheap to post these blobs today on Ethereum. And I don't remember what the numbers were. They were like 2 blobs used, or like 2 to 4 blobs used per block. I don't know. You're nodding your head. Is that,
Yeah, also I think they're planning on, they can scale, because of how erasure codes work nicely, you can scale about 128 times pretty easily without a ton of engineering overhead. So like I don't think native blobs are going to have any issue with like being filled with state, unless like you launch 1 million rollups tomorrow, right?
Right.
It's still pretty underutilized, but also it scales pretty nicely too. So.
Yeah, so we have 9 blobs today, maybe one day soon 128 at some upgrade. And it's underutilized, so it's not clear if we're going to need all that space. Right. Cool. Okay, so any questions so far? Maybe I can...
Yes, between, I guess, rollups and datachains, what stops like a semi-centralized rollup, like say Base, from using like AWS S3 is like, effectively a form of DA with like data availability challenges being like open. I know that.
Yeah. So to my knowledge, they're already doing that. Yeah. And so that's why actually reconstructing the data in most cases is not even, it doesn't matter if it's fast, even in the optimistic case, because most of the time you're just going to ask that rollup service and they're going to give you the data. You're never going to ask the DA chain or most likely you're not going to ask the DA chain, or you're not going to ask the Ethereum blob service, if we want to call it this way, because the rollup service should provide you with the data anyway. And so they do that, right? But the problem is that if one day they stop being honest, or something bad happens to them, then we want to be able to make sure that the data is available, right? It's a single point of failure.
Surely base chains are L3s right now, opposed to S3. Oh, I see. So base itself doesn't post S3. No. Okay. What's this Blobs? Okay.
It's an L3.
They have based chains, and at least the initial proposal had them just posting to S3 through DA. Yeah.
Okay.
One of the options instead of using L3.
They'll give you DA, but it's not actual DA, it's just his S3 bucket. And then they manage the S3 bucket, so unless Base decides like we're going to screw you and not L3 did it. Yeah, that's not real DA.
All right, L3 plus 2 L3, L2 plus 2 S2. There's probably a joke to be made.
Quick question, why do you think there is need for other DAs from the moment that it implemented Blobs? So like I just realized that even Base uses native DA. So why would anyone need like any other DA?
Yeah, I mean, that's a good question. I mean, today on Ethereum, I would think, I don't have the answer, but if you need DA today on Ethereum, then probably you're going to use the Ethereum way. But, these DA chains can be used anywhere, like on any other blockchain. So other blockchains have rollups as well. Maybe there's other use cases that I'm not thinking about. But to my knowledge, the main use case is rollups for these DA chains.
So what does mean that days, 30 days, 19 days over there? Yeah.
30 days? Yeah.
Or hosting or...
The data is basically after 30 days, these nodes can prune the data. They're not required to store the data anymore. So you basically have 30 days to get it if you want, but after that, it's not a certainty that it's there. Right?
And how they can verify the integrity of the DA, because every data is off-chain with the others DA chain, so how they can verify the integrity.
I mean, so that's what's interesting. So I'm going to talk about that for Ethereum next. For datachains, it's mostly a BFT assumption. I mean, right now,
They have the trust assumption for instance.
the trust assumption is a new trust assumption. It's another consensus. Yeah, it's a BFT consensus. So you can think of it today. To me, it looks a lot like full replication assumption. So at least if there's one honest guy, you're good. They're gonna move to. It sounds like they're gonna move to a sharded. So in this case, we need like more like a BFT thing, exactly like what Walrus is doing. And they have this additional like challenging sampling stuff where you as a node, you can like sort of audit the nodes by like sampling them. And it sounds like I don't know anybody who's doing that, but it sounds like you could also say that for your rollup, you require a bunch of like different guys that have challenged the nodes to also gain even more certainty that the data is available. Yeah.
The data is sharded and it's stored for 14 days, right?
14 days for, okay, good data point. EigenDA, right?
Yes.
I have another
14 days, right?
Yes.
And 30 days is Celestial. Yeah.
What is the difference from the EigenDA and Walrus? Yes, you have different categories.
Walrus is sharded for now, and it's long-term storage. Right. This is short-term storage.
Rollups, I guess.
Optimized.
So not optimized for rollups. It's basically for, I believe it's for Sway mostly. Sway, Sway. How do people know how to pronounce these chains?
It seems like French,
It is, but I don't think they're French, right? So
okay.
I thought it was like a Japanese term. I don't know. Sway.
Is there a case where you would need the data for more than like 14, 18 days? Like you did, where would you like put it?
I mean, yeah. So basically, if you want long-term storage, you would go for these like storage chain or like file chain. I don't know what you call them, like Arweave, CR, Falcon. So, like the sort of argument I heard for these is like, you know, like these dApps, like you always connect to a dApp using a website, like some JavaScript front end, and then one day the guy stopped hosting the JavaScript front end. Well, if you put it on the chain, then you can also everything is on the chain. You know, like your smart contract is on the chain, and the front end to access it is on the chain. I know Arweave as a blog post. You can host blog posts on Arweave, I think, with the mirror, the XYZ. I assume they're using Arweave for that, but I don't know. Cool. All right. Let me move to ETH. I don't know how much time I spent here. Yeah. 30 minutes. All right. Let's get moving then. Ethereum does something very interesting. So what they do is that to me that's where sampling gets really interesting. They do what I think it should be called this way. I'm going to call it this way. I think it makes more sense. It's verifiable sharding. And so they used that in this context of verifiable sharding, where they want to shard these blobs. People post blobs. They only want some people to store some of the data. But they want to do it in a verifiable way, meaning that even when people have stored some of the data, we have pretty good guarantees that if people start losing some of that data, we can still reconstruct it. And I'll draw it, but basically these blobs you can imagine them as like blobs of data like that. You cut them in pieces, and then you send these pieces to different people. This is called dissemination. Dissemination. Oh. And once the data is disseminated, these are nodes. I don't know if. Oh. And this is your blob, your data. You're disseminating it. And if you want to reconstruct it, basically you have to ask the different people for a piece of that data, a shard, and then you can reconstruct it. The way if you do that very naively, it kind of sucks if people start losing, if enough people start losing part of the data here, you can't reconstruct anymore. So what we've done is that we started moving, I shouldn't say we because I have no place in that, but what people have started doing is they started using erasure coding erasure correcting sometimes. So that's sort of the solution, which is to basically encode that data. So instead of sending it directly, we're going to encode it with these erasure correcting codes that I'm going to define soon. You get some data that is much longer, I don't know, 16 times this. I don't know how many times the size. And basically, and then you send these pieces of data to people. You're disseminating this way. And the property of these things is that if you start losing pieces here and there, it doesn't really matter, because as long as you have enough pieces, doesn't matter which pieces you have, you can reconstruct the data. Like these pieces here maybe are enough to reconstruct. So if you're erasing some of the data, people start losing some of the data, then you can reconstruct. The code that I'm the most familiar with and that people use a lot is called Reed-Solomon. I'm not going to spell it because I can never spell it, but Reed-Solomon code is basically, you look at this blob and you see it as a function. Can I use a different, use this. You look at this thing here and you say, okay, it's a function. And these entries in the data are basically evaluation at some point. All right, so you see that at evaluation at some point, you figure out, okay, what is the polynomial such that if I evaluate that polynomial at this point, give me these entries, these elements. You reconstruct that polynomial, and then you evaluate that polynomial at a bunch of different points. Maybe we can evaluate at the same point, it doesn't matter. But we want to zero. You want to start evaluating at new points. And here, I don't know, we have f1000, let's say. And so, okay, what is the degree of that polynomial? I'm going to ask. We constructed that polynomial from 4 evaluation points. What's the degree of that polynomial? Not you. It's free, right? So with 4 evaluation, the degree of f is free. And so how many evaluations? So it's how many evaluations do we need from here? How many shards? Imagine one guy stores like one evaluation. How many folks do we need to talk to be able to reconstruct that polynomial? 4, right? So if I talk to these 4 guys here, or I retrieve these 4 pieces, any 4 pieces, then I can reconstruct that polynomial and I can reconstruct the data by evaluating it at enough points. Does that make sense? I know it makes sense for some people, but does it make sense for everyone? So the way Ethereum works is basically they have they do this Reed-Solomon code. They encode their data, and then they disseminate the data. They give it to different nodes, different validators in their network, in their consensus, and that's the splitting of these things is basically what people think about when they think about sampling. They're sampling the data, and different people are going to store different samples. And then to reconstruct the data, you get it, right? The other thing is that you want to be able to... What should I explain here? The other thing is that you want to do it in a verifiable way as well. Like you want to make sure that when you obtain a sample or a shard, you get an actual correct one. And so here, what we are going to use are what we call, how do we call these things? Code commitment scheme or something like that. So it's something that was defined in basically. So there's this great paper from my co-founder Matthias called Foundation of DAS. I'm not sure what's the name of that paper. Paper. I can't remember exactly the name of that paper, but it creates the framework for data availability sampling. So a lot of people are building on top of that paper, and maybe I'm going to talk more about that one. I told Matthias, my co-founder, that he just wrote like a framework paper for like sort of a new field, so he's going to get infinite citation for the rest of his life. But basically, this sort of explains how you can construct this polynomial, not polynomial commitment scheme, code commitment scheme. Can't remember if that's how they call it, but and the easiest way you can think about it is to use. Should I use different? Let's use some green. The easiest way to think about it is that you can use KZG to commit to this thing, and then when you want to give someone a shard. For example, this one, you give KZG proof plus KZG proof. How many people know what KZG is? Just to know if I. Okay, like half. So I'd say. Okay, we're gonna start getting technical, so it's gonna be harder. But KZG here is basically this trusted setup polynomial commitment scheme. So you can commit to a polynomial. For free, it tells you this polynomial is of a specific degree, which is what Ethereum uses, and is very elegant in a way because you get, you know that it's a correct. Well, I'll talk about that later. But as spoiler alert, you know that it's a correct code because you commit to something that's of degree 3 here. And then when you want to open things, you have to give this proof where you have to do some pairing. Doesn't matter too much, but it's very efficient. Or somewhat efficient, but the proofs are pretty small. And the thing that we don't like too much about that is that it requires a trusted setup. So there's the what? Oh, it's not quantum secure also. So some people care about that. Some other people use hash functions. So if you read the foundation of DAS paper, basically they tell you how you can use KZG or Merkle trees and hash functions to commit to things. So here you can create a Merkle tree of this thing and commit to this thing. But Ethereum decided, okay, let's use KZG, and it works pretty well, and I explain why it works, I guess. But you can sort of get the intuition here that whenever you're going to get a shard, you know it's going to be correct because you're getting a proof. Cool. Maybe I'll take some questions before I go through the whatever I want to talk about next.
So sampling is the idea of challenging nodes that store data on whether they actually have it. Is that correct?
So it's important because that's basically, I think, where most of the confusion is in this DA field, because some people use it more as a way to challenge the network, like you just said, like what we've seen in these protocols.
Like which, for example?
So Arweave was like challenging, like trying to like sample parts of the data in some points. I was explaining Celestia, how as a light node you can like sample different parts to try and see if people really are storing them. So you can ask people for proof that they're storing the data. So you're challenging people. Walrus also does that. So you're like slashing them if they cannot produce some data for you. But in the context of Ethereum, you're really using that as a way to make sure that the data has been disseminated efficiently. So it's been sampled enough times, so we know that the data is available because we know that people didn't get only the first. Like it would suck if people only get the first shard, the last shard, or the first shard. So the fact that you're sampling at random places and making sure the data is disseminated randomly, like enough, is kind of the idea of sampling. Oh.
And the reason they sharded is because like the blob is too large.
Yeah. So you'll see after, but basically we have a bunch of blobs. Like every row here is a blob, and this takes space, so we want to shard all of that. I think now Ethereum is doing full replication right now, so they're storing everything. They're moving to something. By the way, the Ethereum stuff is Blob. It's also known as donk sharding, EIP 488. 4844. I can never remember that one. There's also PeerDAS. Like it has a bunch of different names and a bunch of different. There's 3 milestones, I believe. So right now, full replication.
It's proto-dank sharding full replication, right?
The what?
It's proto-dank sharding full replication, and then dank sharding once they do the actual sharding.
I'm gonna trust you on that.
Yeah, it is.
Proto-dank sharding. Then they're gonna move to people only store columns in these blobs, and then they're gonna move to a system where they're only storing cells of these blobs. So we're moving to a system where we're storing less and less. I'm gonna talk a bit more about that in this part.
And
Yeah.
why do you need it to be like verifiable?
Verifiable in the sense that you know you've disseminated enough times during that sampling. Like you're confident that the data is like available because different people have different shards and it's not the same shard, basically. And the shards are correct. So you know that it's not bullshit that was sent to you. And there's also, I'll define that a bit more when I'm going to talk about that. But there's also this kind of the encoding was done consistently also, but yeah, I'll talk about that.
And there's redundancy there, correct? So like a certain piece of data, it's not just that one person's like node, but it's
Right. Yeah, the whole point of this is that, and especially that this is much larger than the blog, there's redundancy in this data. So people are sort of storing the same stuff over and over.
So when you're in the PeerDAS, you have people having, I guess, either individual cells or columns. How does the reassembling work and who does the reassembling?
So yeah, in PeerDAS, you only get columns. It's not the full scheme. And basically to reassemble, you just have to ask enough columns. And in a column, you have these cells, right? So in this example, if you get 4 of them, you can reconstruct that blob, right?
So is it the person that queries that has to reassemble it, or?
Yeah, I don't even know if they have a way to reassemble, or I don't know what's the API for that. But I know if you go on L2Bits, they talk about rollups there, and they require rollups to have a way to reassemble the data, and so there must be an API, but I don't know what that thing is. Actually, maybe I can talk a bit more about that. So yeah, let me briefly mention that because I think that's interesting. But imagine that you have a zk rollup here and you have a proof of this state transition. The blob that you're referring to here is it's a KZG blob, or it's committed using KZG. So it's in some specific field, and that's probably not the same field that you're using. Like in Starknet, they use Cairo and like some Starks, or you might have like some Plonky2 rollup, or they use a different proof system with a different field, right? And so it's kind of hard for them to use that blob as an input of the proof, so that there's a circuit that verifies this state transition. So what they do is that, what they do in their circuits is that they have a blob, or they have the data, I guess, serialized in their own for their own circuits. Although it has to match the field of KZG, so it's probably non-native arithmetic. This is very implementation detail, but that might be interesting. And to prove that it's the same stuff as what's on Ethereum without having to witness that data in the smart contract, what they do is that they added another instruction that lets you evaluate that blob at a given point. I don't know how to write it, blob z. So here you can present a KZG proof of evaluation of your blob, so that you don't have to, so that you can match that to whatever you evaluated in your circuit, blob prime, let's say, if these evaluations match, you know that they are serializing the same data just because of short ZPL. I'm not going to go too much in detail. If you don't understand what I'm saying, it's okay. If you understand, then you can have that additional information. And so later on, if you're trying to re-execute the state of the blockchain and you don't have that blob, it's okay, because here you'll have a proof that whatever was used in the circuit was something that evaluates to the same stuff we had here with the KZG evaluation. I don't know if that makes sense, but don't want to talk too much about that. My understanding is that you still have to do that with non-native arithmetic, so it's still somewhat expensive, but yeah, so I can get rid of that. Yeah, any questions so far on this? Yeah. Okay, so maybe I can talk about, I'm going to talk about one code that this paper defines. And I'm going to talk about the definition here. But foundation of DAS basically defines these, if I remember correctly, if you want to commit, so remember we want to refer to these blobs, right? So we need to find a way to commit to them with Merkle trees, with KZG, whatever. If you want to commit to these things, you need to find a commitment scheme that's good for what we're trying to do. They define some properties. This is kind of technical and it's not super relevant unless you're trying to prove new schemes or trying to figure out the security of these things. But they have 3 properties. The first property is position binding. Position binding tells you that if I give you something with a proof, so here I give you a KZG proof of this evaluation, I cannot open that commitment. Remember, we have a commitment here. I cannot open that commitment to the same position with a different value. So with KZG, it's pretty easy. With Merkle trees, it's pretty easy to get that property. Yeah, hopefully that makes sense. Position binding. Then they have code binding. To me, this is the one that was a bit more confusing. Basically, if you open a bunch of positions here, and it gives you something that's not a proper encoding, then that's a problem. Then you broke the code binding thing. What does it mean for KZG or like this thing? It would mean, for example, or maybe let's think about if we used a Merkle tree of that. Let's say if I open 5 position here, and I get a polynomial, I interpolate that, and I get a polynomial of degree 4. Then we know there's something that's messed up, because we're supposed to only encode polynomial of degree 3. So, of course, our encoding is wrong, because we didn't properly encode something that was a polynomial of degree 3. That's why I understand this property. For KZG, you sort of get that for free, because what you commit is a polynomial that's already of the correct degree, so you're never going to have that problem. Which is why I think I like KZG. If you talk to Matthias, I think he's more into the hash-based stuff, but yeah, different people like different things, I guess. And there's a last one, which is reconstruction binding, I think. And reconstruction binding is, again, a pretty natural property if you think about it. If you reconstruct from these 4 pieces of these 4 shards, right, and then you reconstruct from 4 other shards, and then you get something different, then you messed up somewhere. Like you don't want to be in a situation where you can recover a different blob depending on what you end up retrieving. So that would be very bad. And that's the natural property of reconstruction binding. I'm not going to mention too much of that. I don't know if that makes sense, but this is kind of a more theoretical, like how do you want to define these things? And whatever erasure correcting code you're going to use and a commitment scheme for these you're going to use, you have to make sure that you prove these properties. That's how you end up doing things. The one encoding that I see being used the most is Reed-Solomon. And so you're taking your blobs, again, you're taking your blobs here and you're making them bigger, basically. But what I'm seeing most and most is people moving to these tensor codes, which is basically you see your data as a matrix. For example, in the context of Ethereum, you can just see the blobs. Every blob is a row, right? This is a blob. I mean, same as here. But if your data was like long, if you only have one piece of data, you could just cut your data and put chunks in this blob. Then you, I'm going to use different colors. Then you can encode the rows. By the way, here I'm just extending the data by encoding things. Usually when I do that, it means the code is systematic. It's not very important, but if I encode this data and I look at the, I don't know, maybe the first 4 shards, and it's exactly the same as my data, then you have a systematic code. And usually we like that because if you want to read the data, you only have to recover the sum of the stuff, and you can read whatever you want. I believe most people are using systematic codes where the data can be found, the original data can be found in the encoding. Yeah? It's not very important, so I'm going to stop mentioning it. It's just a tidbit. All right, and so we extended each rows, right? So we encoded these rows, and then we're going to encode the columns. So for example, if you take a column here, you can encode it, and it gives you this longer stuff. And this is what they call tensor encoding, or 2D. I mean, it makes more sense. 2D encoding, 2-dimensional. So if you see that as 1-dimensional, you just have a vector. You're making it bigger. Here, you're making them bigger horizontally and vertically. So that's 2-dimensional, 1-dimensional. So this paper has a scheme that's like that, but I've seen different variants of these. I've seen variants where basically where you would commit to you would commit to these columns, but you would only commit to the data, the original data, these columns. And then you can obtain commitments for these extra columns here by just taking linear combinations. Or in the context of this paper, they also commit to the extended columns. So you have commitments for all the columns. Or what you could do is have commitments for the columns and for the rows. So there's different variants with different trade-offs. Maybe I should also mention, there's these other schemes actually. More recently, there's Zoda. I probably should mention that one. I'm not going to talk about that one, but if you guys stick around, we can talk about it after. Zoda basically uses a tensor encoding, and but not with KZG, with like Merkle tree commitments, and so it has to prove that what you get are consistent encodings in different ways. With KZG, I like it because it's pretty simple. You get a lot of properties for free almost, and so I think that's the last thing I'm going to talk about is how does this tensor code stuff work with KZG. Does that encoding make sense for everyone? Is that?
Can you TLDR why there's an extension again, or why do you extend rows?
You're extending. When you're encoding something, you're stretching the data. You can see that this way. You can imagine that I'm stretching the data here in 2 dimensions, like the data horizontally and vertically. I also briefly mentioned that I'm stretching it while preserving the original data, which is a way of encoding. It's called a systematic code.
So it's like if you don't stretch it, then you lose one of those pieces of data, you're screwed. Right? Like if you have 1,000 data points and you lose one of them, fuck. If you extend it, then you lose one of them, it's like, because you can recreate it, right?
Right. Encoding gets you, it's okay if you lose some stuff if you have erasure, because if you lose some stuff, you can recover from other pieces of data. All right, no other questions? Yeah?
Going about tensor code, how do other, erasure-correcting like things like linear codes, example linear coding, like fit the DA ahead of other more advanced forms of erasure coding, like relative to read solving.
I don't know too much about that, so I'm not. Yeah,
Okay.
I don't know. Maybe some people don't, but I think sometimes people use. So there's this paper called twin codes, and they use a different encoding for the rows and then for the columns. Yeah, I don't know. But yeah, let's not talk about that. Maybe another time. All right. So I explained here the thing that doesn't work right away. So I said it. When you commit using KZG here, the nice thing is that running out of colors. When you commit to the columns here using KZG, the nice thing is that you get a correct encoding. Because remember, you commit to this thing basically. So when you open a position here, you know it's going to be correct. You know your whole column is going to be correct. And in this context, you can think of like you're someone sampling or receiving a shard of the data, and what you're getting is a column, or maybe a cell in the column. But you want to see if it's correct. You know it's correct because of KZG. Now, what's not clear is that if we look at the extended data here, and if we look at these cells, we don't know if these values are. We know these values are correct encoding of these values, right? But we don't know if these values are a part of a correct encoding of the rows. This could be bullshit data, the green stuff here, is what I'm saying. If we had a KZG commitment, we would know that it's fine. Since we don't have a KZG commitment, this data could be any garbage that you can imagine. So there's different ways. Does that make sense? Yeah. So there's different ways of fixing that. Having commitments of the rows, again, it would be one way. But what they do in this paper is that they notice that, I never know how to explain that one, but maybe I'll make more room. All right, this is the last thing I'm going to explain. So that's a bit more involved, but like we have to think about matrices. When we think of linear codes, and Reed-Solomon is a linear code, basically what you're doing is that you have a matrix, let's call it matrix G, and then you have your data, let's call it M, or it could be a vector, maybe let's call it, doesn't have to be multiple vectors, could be just one vector. And what you end up with is an extension of that. So this is your message, what you end up with is a code. So we can, just trust me, we can write things with matrices. Encoding something like that is basically a matrix multiplication, and we get these codes. As you can see, the data was extended. When you have this kind of linear codes, you have something that's called a parity matrix. And H. If you multiply the parity matrix with G, or if you multiply it really with any code, any correct encoding, you get 0. Here you would get, sure. And here you would get a vector of 0. Right? Have to think of a shape of matrices. So, and H is this parity matrix. So just trust me, these parity matrices exist for any linear codes. Reed-Solomon is linear code, so we have this, what we call, maybe it's important also to mention it, these are called generating matrix, I think, for the code. And so if we want to check that these rows are a valid encoding, we can look at them as vectors that we want to test using that parity matrix. If we multiply that parity matrix with with these vectors, basically, it should give us 0 if they're correct encodings. Since here we have rows instead of columns, we have to massage that a bit. So we get the, I don't know, M prime, because it's extended. Or let's call it C, actually. That's our code. So that's the example there. And the H is going to be on the other direction. So we have H transpose, because we're trying to, here when we produce this matrix, we're taking the rows and the columns of these, right, columns, rows and columns. Here we're trying to take the rows. So we need to, yeah, more like this. And we want to check that this gives us 0. Why did I? Oh yeah. So we're going to take the columns. Maybe I should use a different color. Oh. Basically, whenever you look at this, you have to think that these are all the, you're doing inner products, basically, between, we're doing inner products between the rows of my code, of my encoding, and the columns of my parity matrix. And every cell that you get here, every little cell, is going to be one of these linear combinations. These, yeah, you can see that one of these inner products. So you're taking all of the vectors in this parity matrix, and you're always going to get 0 for this, for any row that you take in your code, for any encoding. Should be 0. Now what they do here is that they're like, okay, we can do that with commitments, and so we're going to take, let me use some black. Since we have commitments of these, we're gonna take this linear combination of commitments, and we're gonna check if this gives us a commitment to, well, this is not a commitment. Basically, so there's one more step, and it's gonna be clear. But I want to check if an entire row of these cells is 0. What I can do is I can take a random linear combination. If all of these cells are 0, then the random linear combination is going to be 0. So what we do is we sample this vector A, and we multiply it here. So we're going to get a row here. This entry is going to be this row times the random values, random. And this is going to be 0 with high probability if all of these cells are zeros. So now we're adding this vector A here. So this is really the check that we're doing. And the only thing I'll say is that because we have commitments here, basically what we can end up doing is compute that first. We get some vector, and now the only thing we're really doing is taking a random linear, we're doing a linear combination of our commitments. And because we're doing a linear combination of our commitments, we can just do that with the commitments we have. So we end up having something that looks like, something times commitment 1 plus something times the other commitment plus something times this commitment. And at the end, what you're expecting is a commitment of 0. It's a commitment of this. And we know what the commitment of 0 is. With KZG, it's pretty easy to compute. And so that's the check. And I think they call it the homomorphic check. Doesn't matter too much. But if you think about it, and if you think about matrices, you'll get there. But the whole idea is we don't know if these extended columns are correct encodings. Turns out that if we do a matrix multiplication with the parity matrix, we can check that it's 0. And we can do that without opening commitments, just using the commitments by just doing a random linear combination of the result. And this works. Maybe, I hope I convinced you, but cool. I think I'm gonna stop here, and we can stop the video here, and I can take questions. Yeah.